So the question is like this. A toroid has a core of inner radius 25 centimeter and outer radius so like this they will give two things. So for this 26 centimeters they have given. Now if they give like this, you got to take the mean of the radius, okay, around which 3500 turns of a wire is wound. Now what is the difference between the solenoid and toroid, you will understand. You see that this radii is much larger. In the case of solenoids, we have taken only the radius is about 1 centimeter. Now you see the toroid, the radius is 25 centimeters, 26 centimeters. So it's 25 times more than the solenoid. Solenoid is a small one and the toroid is a larger one, larger magnetic fields. The next thing is, you see the number of turns, that is about 3500 in the case of toroid. The solenoid problem, we have seen the turns about 1200, the max. Okay, 500 turns, 1200, 120, not even 1200, 120 turns. That is a few hundred turns, less than 1000 turns for the solenoid. In the case of toroid, you see 3500 turns. The number of turns are more. So it produces more amount of magnetic field, obviously. So around 3500 turns of a wire is wound. If a current of 11 amps, if a current of 11 amps is passing through the wire, the current of 11 amps is passing through the wire, what is the magnetic field? What's the magnetic field? What's the magnetic field outside the toroid? First part is outside the toroid. Outside the toroid. The part 2 is that you have inside the core of the toroid. Inside the core of toroid. The third part is in the empty space surrounded by the toroid. In the empty space surrounded by the toroid. So I'll show you the regions. What are the regions? So here the answer wise, what is I? The current is about 11 amps. And the number of turns, that is capital N, that is 3500 turns they have given. N is 3500. The next is the mean radius. Mean radius is average of these two, that is 25 plus 26 by 2. So ID plus OD by 2, that's how you had to do. So 25 plus 26, what you get is 25.5. That is the mean radius, 25.5 centimeters. Okay. So that is 25.5 into 10 to the power of minus 2 meters. Convert it into meters. Now total length of the toroid. See, the value of N for the toroid is N by 2 pi r. Remember this. So N is 3500 divided by 2 into, we'll put 22 by 7 into R. R is 25.5 into 10 to the power of minus 2. Okay, into 10 to the power of minus 2. Plug in this. So when you do that, you will get about 51 pi into 51 pi, okay, into 10 power minus 2. Oh, sorry, this is n by 2 pi. Sorry, you will get okay, 3500 divided by, so any terms will cancel. So we can cancel this about, okay, you can give the cancellation, try it out. So 3500 into twice 7 will put it, okay, no problem. So it's 44 into 25.5 into 10 to the power of minus 2. So someone can take a calculator and then check this out, how much will be the answer, this one. So this part we got. Now the first part, always we assume field outside toroid is 0. This is like solenoid, field outside toroid is 0. This is how we consider. Okay, first part. Second part, field inside the toroid. Okay, field inside the toroid, inside the core of toroid, inside core of toroid. So that is mu naught ni. So you can work out these numbers, mu naught ni. So mu naught is 4 pi into 10 to the power of minus 7 into n value is, you can plug in that 3500 into 7 whole divided by 44 into 25.5 into 10 power minus 2, and that I is 11 amps. 11 amps, no? So 11 you can put, you can find out this value. This value works out to be 3.02 into 10 power minus 2 Tesla. That is 3.02 into 10 to the power of minus 2 Tesla. This will be the second part. The third part is again in the empty space surrounded by toroid, that is again 0. So these are the three things which you have to remember. You can make a note. After that, you can tell me. Once finished, please let me know, ma.
Noted, sir.
Okay, good. So anyway, if someone who has come just now, don't worry, you will get the record. So force on a moving charge in a uniform magnetic field. Now let's assume this situation that there is a magnetic field like this. If I put a cross, the magnetic field is going inside the plane of the paper or plane of the board. Now the scenario is that there is a charge. I will not mark like this. You can mark like this also. Okay. This is a region where the magnetic field is there. Imagine a charge is circulating like this. Okay. A charge of minus q is circulating like this. And here if I put dots, that means the field is coming out of the situation. You can assume any kind of situation, doesn't matter. Now if q is moving like this, it is moving in a circle, means there is some centripetal force. The centripetal force is responsible for the movement. What is creating the centripetal force is the magnetic field. Okay. Now uh, in this case when the charge is moving in a circular path, in this case when the charge is moving in a circular path, the velocity and the magnetic field, velocity of what? Velocity of charged particle and the magnetic field are perpendicular to each other. And you know that work done by centripetal force is zero. So work done is zero. Work done is equal to zero by the magnetic field. Because work done by centripetal force is zero. So this one point, please note. As you know, why it is so? As work done by centripetal force is equal to zero. Why this is so? Because if you think that this is the direction of the velocity, this is how the centripetal force acts, and the work done is product of force into displacement and the velocity will have same direction. So but these two are in 90 degrees, acting force and the displacement are at 90 degrees, means work done is zero. So work done by centripetal force is zero. Okay, so this point you keep in mind. Yeah, I'll wait. So please note it. After that I'll write.
Noted, sir.
Magnetic, please change magnetic force here. Magnetic force. Please note it. Magnetic, not magnetic field, it's the magnetic force actually. Magnetic force are perpendicular. This is the force, not field. There is a difference between the force and field. So the force is, there is small variation. Mu naught by 4 pi, you have for the magnetic force m1 m2 by d square. But the field wise, we divide with one of the pole strength. If we divide with one of the pole strength, what I get the field. Okay, it will be like mu naught by 4 pi into m by d square. It will be like this. Small variation is there between the field and the force. The magnetic field, see, magnetic field is measured in Tesla and the force is measured in newtons. So what is actually Tesla is actually Newton divided by, this is the magnetic pole strength is ampere into meter. It is something like this, a different kind of unit. It is ampere meter, something like this. You get a unit, ampere meter. That's called a pole strength. You will learn that later, how these two are different. M is called the magnetic pole strength. It is having the units of ampere meter. Ampere into meter. So it's the same unit of current times meter. So it's a different thing that is called pole strength. So you will learn that later. Don't worry much about that. 1 Tesla is Newton by ampere meter. So this Tesla is like 1 Tesla is 1 Newton ampere inverse meter inverse. That is Tesla. Then you will be familiar. You will become familiar with the Tesla unit. You are familiar with the newtons, amperes, and meters. In Newton by ampere meter is Tesla. So that's what it is. Once finished, please let me know. Of course, magnetic field is also perpendicular to the velocity. That is next thing. We will understand that.
Done, sir.
Okay, good. Now we have, when a charged particle Q, when a charged particle Q moves with the velocity v, moves with a velocity v inside a uniform magnetic field B, inside a uniform magnetic field D, the force experienced, then the force experienced by the charged particle, by the charged particle, or force acting on it, or you can say force acting on it, is given by F bar is equal to Q into V bar cross B bar. Okay. Now how to take the direction? Suppose you take the situation like this. So I'll introduce again to you the cross products. Suppose A bar and B bar is there. This is the angle theta. And how to show the cross product? Okay. A bar should be aligned with B bar. So you turn this way, and that's the corpus screw rule. Okay. This is the corpus screw when you turn this like this. So this is how you can put a screwdriver like this. So what is the corpus screw rule? You put a screwdriver like this, and imagine a screw you are turning upwards. When you turn upwards, the A fix B, you fix B, and when you turn the screw upwards, it will the A which will be turning towards B, and that's A bar cross B bar. Okay. When similarly B bar cross B bar refers to the situation where here both are at 90 degrees. This is my B bar. This is my B bar. Both are at 90. When I turn V bar to B bar, the force is given by right hand thumb rule or the corkscrew rule. So this is the direction of the force F bar. This is the cross product. So here you have to assume that how to take the cross product, how to take the thing. You draw A bar and B bar like this. Okay, A bar and B bar like this. You align A bar with B bar. So it's like align A bar with B bar. For that, how do you turn the screw? That's all you have to check. How do you turn the screw? So you turn the screw in clockwise direction. When you turn the screw clockwise, the screw moves up. That's how you fasten the screw. That's the direction of A bar cross B bar. Similar this way, you will find V bar cross B bar this way. This is the F bar. Clear, I hope. So once finished, please let me know.
Done, sir.
Okay. Now the next part. From you can say from the right hand from the right hand thumb rule from the right hand thumb rule, F bar is perpendicular to both V bar and B bar. V bar and B bar. And hence hence it changes and hence it changes changes the path continuously and F bar acts as centripetal force, which keeps the charged particle always in circular motion, which keeps the particle always in circular motion, which keeps the particle always in the circular motion. So this part, please note. So after this, I will tell you another point. This is an important question actually. After this is an important question. Please note it. This is finished. Finished? Everyone?
Sir.
Yeah. Yeah. Okay. The next one. When this is a question, when a charged particle undergoes or travels in helical path. So this is a question, very important question. When V bar and B bar are not perpendicular to each other, when B bar and B bar are not perpendicular to each other, that means that is the angle between V bar and B bar is not 90 degrees. In that condition, okay, in this condition, the charged particle follows helical path. In this condition, the charged particle follows helical path. So helical motion will be like this. It will be like this. Okay. This is called helical motion. This kind of pattern. Okay. This kind of pattern is called helical motion. So it's like a spring. So if it follows like a spring, that is called a helix. That's called a helical motion. This is called helical motion. X. This is Y. This is Z. Helical motion. Helical motion. Next, one more point you can note, it is always the perpendicular component of velocity it is always the perpendicular component of velocity responsible for circular motion. These are very, very important points. It is always the perpendicular component of velocity which is responsible for the circular motion. Once finished, I think we'll have a timeout. I will not start. Once finished, please let me know. You may have to log in once again. Is this clear? Noted.
Wait, sir, wait.
Yeah.
Done, sir.
Okay. Anyway, please log in once again. I'll be closing this.